Hello, everybody again, and welcome to this learning unit about modeling and forecasting of time series. So what we will see today is first, what do we actually mean by forecasting a time series? Then we will have a look at three models, three classes of models. So autoregressive models, moving average, and Arima models. And then we will see how to choose the parameters of Arima models. So we have seen in the previous learning unit that with time series, basically, we want on one hand to identify the patterns of these time series, like, for example, trend, seasonality, and autocorrelation. And on the other hand, using these patterns in order to forecast future values of a series. We focus on this forecasting now. Of course, we cannot aim to have exact predictions because in the end, we are dealing with random quantities. So it's not possible, for example, to know exactly the value tomorrow of a stock. But we can aim to give a probability, at least, of future values of our time series. In order to do this, we want to let's say, state a model for our time series. And in particular, to model the value of a time series y at t as a function of, on one hand, previous values of y, on the other hand, maybe some what we call random errors of random residuals, let's say realizations of a white noise time series, or also in some models as a function of exogenous variables. So we can do it having a look also at the pattern analysis we have seen in the previous learning unit. Let's start from autoregressive models. So the idea is to focus on previous values of a time series, right? So we have seen before that we want to model y as maybe a function of previous values. Here from y1 to yt minus 1, then usually only the last one are used. And this is exactly what we do now. So we express yt as a linear combination of the past values up to time t minus 1. So we have a linear constant term c. Then this combination up to yt minus p, where p is called the order of these autoregressive models. And then this term epsilon, that is a realization at time t of a white noise time series. So a stationary time series. The parameters phi I are in R, but if we want the series to be stationary, they have to satisfy some additional requirements. We will see later. We write this y, defined here, as an ARP model, so autoregressive model of order P. AR1 model are defined as the sum of a constant plus phi1 yt minus 1 plus the error epsilon t, and it is stationary if and only if the absolute value of phi1 is strictly less than 1. This is something that we have also seen, if you remember, in the last part of our previous learning unit. So let's focus on the behavior now of these AR1 models. If you think about it, if phi1 is equal 0, then you don't have epsilon t minus 1, so yt is only a constant plus a white noise series, so it's a white noise series. If phi1 is equal 1, you have a random walk, so a random walk has a series whose differences are stationary. So, and this is the case because yt minus 1 is equal to c plus epsilon t, so white noise. And if phi is strictly less than 0, so strictly positive, negative, it is mean reverting, so it oscillates around the mean. AR2 models instead are defined adding a term depending on yt minus 2. It is stationary if and only if phi2 has absolute value strictly smaller than 1, the sum of phi1 and phi2 is strictly smaller than 1, and also the difference. The stationary conditions for order is strictly bigger than 2 are instead more complex to derive, but you can have them, for example, with Python, R, and other languages. Now, I wanted to show you also two plots, one for AR1, one from AR2, taken from the book, the online book, Forecasting Principles and Practice of Heinemann and Athanasopoulos. Here we have AR1 with the constant 18, phi1 minus 0.8, and here AR2 with the constant 8, phi1 1.3, and phi2 minus 0.7. And you can see that they look stationary. They are actually stationary because these parameters satisfy the condition we have seen. Now, let's move to moving average models. Moving average models, in moving average models, YT is not expressed as a function of the past values, but of the past errors. So formalized, you have the constant C plus the error at time t, as it was the case for autoregressive processes, plus a linear combination via parameters psi in R of the past errors. So here Q is the order of the moving average, so we arrive to T minus Q, and these parameters might satisfy some conditions if we require a process to be invertible, in a sense that I will specify later. So here again, we refer to Y as an MAQ model, so moving average model of order Q. And you can see that this Y can be thought as a weighted moving average of the past Q errors. So you remember in the last learning unit, we have seen that we assume these weighted moving averages when computing the trend. And here two plots, again, taken from the same source with the parameters you see here. Now, we have seen for now finite orders P and Q for autoregressive and moving average models. We can define also infinity autoregressive and moving average models, so with infinite order, but with some conditions. So model Y is called moving average infinity if it can be written as at time t the sum of the constant of the error in t plus the sum of delays of errors t minus j, epsilon t minus j, times parameters psi bar j. I call these parameters psi bar instead of psi because they have they're not the same psi as before because they have another index with respect to the error, and the sum of their absolute value must be finite. Same thing for the autoregressive models. Okay, so the, here we have phi, and the absolute value of phi when summed must be finite. How to move now from an autoregressive model of order P to a moving average model of order infinity. So how to express an autoregressive model as a moving average model. We see how to do it with the autoregressive model of order 1, as you see here. So basically the idea is that you can express yt as phi1 yt minus 1 plus epsilon t. You can express yt minus 1 as phi1 yt minus 2 plus epsilon t minus 1. So you get this expression here. Moving then one step further, you get the sum of phi to the power of 3 yt minus 3 plus phi1 power of 2 epsilon t minus 2 plus phi1 epsilon t minus 1 plus epsilon t. And so going further, we obtain an infinite sum, or let's say a sum with infinite terms of the type phi1k, phi1 to the power of k times epsilon t minus k. And this converges, this is less than infinity, if and only if the absolute value of phi1 is smaller than 1. So if and only if this process y is stationary. This is true in general, in the sense that every AR model can be expressed as a moving average infinity model, if and only if it is stationary. So now we can also express, maybe in some cases, moving average models as autoregressive models of order infinity. And such processes are called to be invertible. So, for example, a moving average model of order 1 is invertible. That is, it can be expressed as an autoregressive model of order infinity, if and only if psi1 has absolute values strictly smaller than 1. And this can be seen expressing epsilon t in this way. You can, if you want, try to check why this is true, but okay, it is not that important now. A2 model are invertible if these conditions hold for psi, and are similar conditions to the one that make autoregressive model infinity stationary, but not exactly the same. So now let's go to Arima models. Arima models are a kind of combination of moving average models and autoregressive models plus differencing. So Arima stands for autoregressive integrated model, autoregressive integrated moving average model. And here the point is that we don't model directly y, but the difference y. So we model yt minus yt minus d, where d is the order of differencing we take. So we call an Arima PDQ model a model where this difference between yt and yt minus d can be expressed as a constant plus linear combination of past differences. So this is, for example, the difference between yt minus 1 and yt minus d minus 1 up to order p, plus lagged errors with parameters psi, plus the error at time t. So you have basically the combination of a kind of autoregressive model of order p, taking into consideration anyway that you have also the difference, and a moving average model of order q. If you want your model to be stationary, then you have to take the same conditions that let a moving average model invertible and an autoregressive model stationary. So some examples. If you have that P, D, and Q are 0, then you have white noise because you are left with C plus the error epsilon t. If only D is 1 and P and Q are 0, then basically you have that yt minus 1 is equal to C plus epsilon t, so it's a random walk. If both D and Q are 0 and P is not 0, then you have an autoregressive model of order P, because this is yt, this is yt minus 1, this is yt minus P, and you don't have these terms. On the contrary, if P is 0 and Q is positive, then you have a moving average model of order Q. So what if we want also to take into consideration seasonality? Then we have the so-called seasonal Arima models, also called SARIMA, seasonal Arima. Sorry, and here you had 4 more parameters that are the capitalized P, D, and Q, and the seasonality order M. What does it mean? So a Arima model, PDQ and then capitalized PDQ and then seasonality order M can be written in the following way. So this is maybe the most technical part of my presentation, but well, let's have a look. Let's start from this term, yt minus d minus the difference between yt minus m and yt minus d minus m. This is the usual difference with order d. This is the difference of the seasonality term, because you take minus m, you shift of m periods if you have a seasonality m. So if you have a weekly seasonality, then m is equal 7. Now, which operator do we apply? We have, first of all, define b as an operator of one leg, okay? So applied to yt, it is yt minus 1. Then bm applied at yt is yt minus m. So m legs. Capital phi applied to bm is 1 minus phi1 bm. Okay, so phi capital bm yt would be yt minus phi1 yt minus m, and then up to phi p bpm. What does it mean, bpm? With pm in epics, it means that y gets legged of p times m periods. So from yt to yt minus pm. Phi b is a bit less complex, so it is 1 minus phi1b minus phi q bp. So p legs here. Then psi capital bm is same thing as phi capital, but up to q, and so up to bqm, and psi same thing as phi, but up to q. Okay, so you have these orders, q capital q, p capital p, that are respectively the orders of seasonal and normal, moving average, and autoregressive models. Just an example in order to make things a bit clearer, I hope. Arima 011-0114 model. You have yt minus 1, yt minus 1 minus yt minus 4, yt minus 5, because m is equal 5, and here these are just ones, because both capital P and P are 0, are equal to, now let's focus on this part. You apply what to yt? Epsilon t. So here you have psi b, that is 1 minus psi 1 b. That's it. Psi capital bm is 1 minus psi 1 b4. That's it. And then what do you have? When you apply 1 minus psi 1 b to epsilon t, you get epsilon t minus psi 1 epsilon t minus 1. Then you apply this, and you get epsilon t minus psi 1 epsilon t minus 1, left as it is from 1, minus psi 1 epsilon t minus 4, minus psi 1 minus psi 1 not capitalized, that makes plus psi 1 capitalized, epsilon t minus 1 legged of 4 more, and so epsilon t minus 5. Okay. So this is our example. Now we can also include exogenous variables to these models. So like taking x, so k variables x1 to xk, exogenous, so coming from outside the model, let's say, we take their value at time t, and multiplying them by some constants alpha k, we have this linear term that gets added in the model. So like here on the right, for example. If you want also to have some other sources influencing our model. Then last big topic, how to choose the parameters of Arima models. So in the end, we have a bunch of parameters we have to choose, right? Well, the linear parameter, this is quite easy because you see if it has an intercept or not. So I don't focus on it now. Then you have to decide, just focus on Arima, okay, not Sarima. The differencing order, D, then the auto regressive part order P, and the moving average part order Q, and then also these coefficients phi1, phi p, psi1, psi q. So what's the point? What's the scheme? What's the first element you have to estimate? Well, the first one should be always the order of the difference, D. Looking at autocorrelations, I will show you later. Then you get P and Q, looking either at autocorrelation function or partial autocorrelation function plots, or to AC or BIC criterion. And finally, you get the parameters by maximum likelihood estimation. So this is the order, but now let's see in detail how to do it. Let's start from the differencing order. As a general rule, the differencing order you choose is the lowest order of differencing, such that the series differenced is stationary. In the sense that if you see that the original series is stationary, then you don't need to difference at all, and then you take d equals 0. If you see that it has a constant average trend, then you take d equal 1. If this trend is also moving with respect to time, you take d equal 2. Usually you don't take d from 3 on. So how to see if a series is stationary? So if y stationary, or then y prime, or then y prime prime is stationary. So you have to see that the autocorrelation function plot decays rapidly to 0. If instead you see some autocorrelations that are still positive after a high number of legs, then this means that you have to differentiate. Anyway, you don't have to exaggerate, because a common error is to over-difference. Okay, so to take d too big. That's something to note. So we have seen how to estimate d, let's say. There are two ways to estimate P and Q. If you're lucky, and then I will specify further what does lucky mean, you can use autocorrelation function and partial autocorrelation function plots. Otherwise, you have to use this AIC or BIC criterion that we will see later. ACF and PACF plots, you remember, so the first one shows the correlations between y and its k-legged values for moving k. The PACF plot does the same, but removing the effects of the legs up to k-1. They can be useful if either Q is 0 or P is 0. So for Arima PD0 or Arima 0DQ models. You can say that Y is an Arima PD0 model if you see that the ACF is exponentially decaying or sinusoidal, and in this case you can say that Q is 0, and if there is a significant spike at P, but no spikes later than P. Sorry, no spike beyond P. So for P plus 1, P plus 2. On the contrary, you can state that P0 if the PACF is exponentially decaying or sinusoidal, and then you choose Q if there is a significant spike at Q and no one beyond Q. But what if both P and Q are not 0? So what if you don't note these or these? Well, then you have to use the archaic information criterion or the Bayesian information criterion. Archaic information criterion says that you have to choose the model that minimizes the AIC value that is equal to 2 times the number of parameters in the model. So you want to let this number be small. minus to the logarithm of L. L is the likelihood function of the model, which is defined as the joint probability of the data as a function of parameters models. So the bigger it is, the better it is. So the smaller minus logarithm of L is, the better it is. BIC is the same, but you multiply k not by 2, but by the logarithm of data you observe in the model. So in our case, the number of data is the number of times we observe. So in our case, the number of parameters is p, because you have the phi's, right? Phi1 to phi p. Q, psi1 to psi q. One parameter that is d. And if c is different from 0, then you have to add 1 parameter. If it is 0, then you don't have it, and you don't add it. BIC, then same thing, but you don't have 2, but logarithm of t, number of times observed. And so you choose P and Q that minimizes BIC or AIC. Then how to estimate the parameters C, phi1, phi p, psi1, psi q. Well, C can be the intercept. So this can be estimated also in some easier way, but you can estimate it also together with the others via a maximum likelihood estimation. Okay, so basically you find the value of the parameters that maximize the probability of obtaining the data we observe. Then let's say you have estimated all these parameters, P, D, Q, and phi, psi. How to see, and you get a model, right? How to see how good it is? Well, a good model must let's say get good forecast. Okay, not exactly, we cannot aim to have exactly forecast. We will have an error with respect to the true ones, but still we want to minimize this error. So what you do is you take a sample of data. You use 80% of this data to do what we have seen, estimate the parameters, and the other to test these parameters. In which way? So let's call the set of tests the calligraphic t-test. This is the number of its elements. For every t in t-test, you compute the error, not to be confused with the random error epsilon t, the error yt, that is the true value of y times t, minus the forecast you would get with your parameters p, d, q, phi, psi. Then you take once either the average of the absolute value of the error or the square root of the average of the squares. If this is small or this is small, your model works well. Otherwise, you have to change. So this is all. Again, the main reference is this very nice book, Forecasting Principles and Practice, from Heinemann and Anasopoulos. I thank you for your attention, and I invite you once more to write me if you have any questions. So thank you and have a nice day.